14 minus 4, I get 10. About here, where's the pencil? I get this. Okay, I hope everybody's following me. So I've decided to make the potential difference equal to 4 volts. Okay, I wanted 10 before, but then I realized that with 10 I'm not going to have many equipotential curves. So then I changed, I think, to 5, and with 5 I realized that I would have only 6 equipotential curves at most. So if I start with 30, so maybe that's not a good choice. So now I've decided to make it 4, sorry. Potential difference delta V equal to 4. So that's why I've drawn these successive equipotential curves of a electric potential of 30, and then 28, and then 22, and then 18, and then 14, and then 10. Okay, so after 10, of course, I should have an electric potential curve with a electric potential of 6, because 10 minus 4 is 6. So that's gonna be here. Press the pencil, I get this, and then the last one will be 2, because 6 minus 4 is 2. So where is 2 gonna be? It's gonna be far away. Yeah, about here. Yeah, perfect. Of 2. Here they are. Okay. So I have a whole bunch of equipotential curves. Equipotential means, of course, that the potential is the same everywhere. Okay, like for this one of 2, if I move the voltage probe box, see that it remains, electric potential stays as 2. Okay, on the curve it remains 2. Alright, so you understand that. Okay, so now what are we supposed to do? So you see that you're supposed to answer the following question. In regions where the equipotential curves are closer together, is the electric field stronger or weaker? Okay, so where are the equipotential curves close together? Okay, to me it seems they are here. It's here. It's at this position. I hope you can see it with the cursor. Okay, here, close to the charge. Close to the charge. So is the electric field strong or weak there? Okay. To determine that, you can use the sensor. Okay, I have the sensor here. To draw the electric field. Okay, so this is the electric field. I don't know if you can see it. So you see, this is the electric field. It's the red arrow is the electric field. It's very long because the electric field is pretty intense close to the charge. So maybe let me move it to a far away from the charge so that you can see what the vector looks like. Okay, so sensor. Let's remove it from the box. Put it here. Okay, so I want to measure the electric field here, where the yellow dot is, and this is it. Okay, so this is the electric field. It has a magnitude of 1.53 volt per meter. Okay, so that the arrow is short, relatively short, and it shows you the direction. Okay, minus 175.6 degrees. Okay, a different location. Let me put it closer. As I move closer, the electric field vector becomes longer. Just this red arrow becomes longer. well, I can't really read. Okay, here. So 4.58 volts per meter. Okay, so that's the magnitude of the electric field. All right. A different place. You see, as I move closer, it becomes longer. 11.7 volts per meter, and this is the 126.9 degrees is the direction, of course. Okay. So that's the angle between the positive x-axis and the vector itself. Okay. As I move closer, you see that the arrow becomes longer, and of course the magnitude becomes longer too. Okay. So I can do that for different positions. Okay. So okay, let me see. Like here, I have the electric field. So that's this red arrow. So I'm pretty close to the charge. I can move to another location where, so let me, sorry about this, take the sensor again and place it somewhere else at another equipotential or here, and I get this electric field. Okay, so this arrow. Take another one, sensor from the box at the bottom, and measure the electric field. So 4.58 volts per meter. Another one. Small. I can barely see the arrowhead. Okay. Very small electric field with a magnitude of 0.72 volts per meter. Okay. With these few arrows, if you want, you can add a few more. I have another one here. Another one here. Another one here, and so on. So what conclusions do you draw? So that's what the question is asking. What conclusions do you draw? In places, in regions where the equipotential lines, those are the green circles, are close together, is the electric field strong? So basically, is the magnitude high? Or in other words, is the length of the arrow vector that represents the electric field, is that length long or is it short? Okay, so if it's short, of course the electric field is weak, so you have to decide. All right, are there any other questions? I think that's the end of the lab. Yes, I think I've covered all the questions. So if you have any questions, please don't hesitate to send me an email, and I will try to respond to your email as fast as possible. Okay, so I hope this helps, and I'll be waiting for your emails and your lab reports. Thank you for listening, and see you next time. Bye.